Unit 2, Kinematics. Kinematic diagram. Objective: learn what is robot model, learn how to draw kinematic diagram. Section 1, robot model. From the computation point of view, a robot can be viewed as such. We will have a controller and that send out the control signal to actuator and sensor. Then actuator move the manipulator, and manipulator will move some object in the environment, and the sensor will actually sense the location, color, temperature of those objects and actually determine what would be useful for the control. So we send back this information back to process, and it will send back to the control to make decision to tune your actuator and sensors. So this is the computational model. Even though some robot will have different model, we will base on this model to explain how kinematics is related to a robot. So the most important part right here would be the manipulator, and we will talk about it right here using the kinematic diagram. A robot arm is a manipulator. Without a control, without a sensor, without the processing portion, a robot arm receives control signal from an actuator, which can be a remote control, cell phone, PC, mouse, or a feedback system. So a robot arm is manipulated to perform a certain task. It is a manipulator. Kinematic diagram, section 2. A robot arm consists of joints and links. Right here, we have a very simple chart. Joint, we have two joints. So it would be degree of freedom 2 system. We have joint 1 and joint 2. And we have 3 links from the base to joint 1, and then from joint 1 to joint 2, and from joint 2 to end effector. And we have a symbol for revolute joint, prismatic joint, and link. And these are called the 2D diagram for a robot arm or the manipulator. So kinematic diagram can be of 2D model or 3D model. We have already presented the 2D model over here. And for 3-dimensional model, we can draw like this: a block link or a planar link. These are 2 link model and can have a prismatic joint or a revolute joint. So right here, let's look at this robot arm number 1. Robot arm number 1 has a servo right here, servo 1, and there's a servo 2. So this one is a joint 1, and joint 1 is a revolute joint. Joint 2 is over here. It is another revolute joint, and there's no prismatic joint. So basically, this joint 1 will move like this as rotation. Joint 2 will move like this. So basically, your robot arm can actually extend from here to here, make a circle, and then you will actually rotate up here to here. So it will be something that is a donut-shaped motion. So we can draw a 3D diagram like this: the rotational joint number 1, joint number 2. And this is the top view, 2D top view for the same robot arm. And here is the front view for the 2D robot arm. So section 3, assignments of axis. So in order to study a robot arm, just drawing the diagram is not enough. So now let's look at how to assign the axis to each joint. So here, let's look at the Z joint. Z joint is a Z direction, and Z direction is related to the rotation. So since your rotation is here, make a circle like this. So the perpendicular direction is chosen for this revolute joint. The joint 1 here, it will make a rotation like this, or the other way is. So the perpendicular direction is chosen for Z1 in this direction. And the red dot is used as the end effector. End effector is the final point that you reach the target. Now, let's look at the joint X. At the revolute joint, we actually create a kinematic frame to describe the coordinate. So basically, each point, we would have X, Y, Z, 3 axes. So right here, in this frame over here, we have Z this direction, we have already decided. And then X this direction, Y this direction. Y is into the paper. So here we have Z is out of the paper, X in this direction, and Y in this direction. So each one of these is perpendicular to each other. We create two frame system. And we use right-hand rule. So right-hand rule, let's look at this handbag. It will be something like this. And then we have the hand palm. This is also right hand. And we use this symbol. So we have the arrow. This handbag system, it is actually into the paper. So it's into the paper, just see the arrow end. And then if we are using hand palm, and Z will be out of paper, and then we see a dot. So these are the right-hand rules. So right-hand rule also show that this, you have X, Y, Z. A or X is the direction that your finger pointing to. B is your palm's direction, or your middle fingers pointing to, the direction you pointed to, or using Y. And Z will be your thumb direction, and we call this the right-hand rule. Actually, it is also true for any vector cross product. So basically, you have A vector cross product with B vector, and you will get A cross B, that would be your cross product direction. To assign the axes, we have 4 rules. Rule number 1, the Z axis must be the axis of rotation for revolute joint, or the direction of motion for a prismatic joint. Rule number 2, x-axis. The x-axis must be the perpendicular direction both to its own Z direction and the Z axis of the frames before it. Rule number 3, all frames must follow the right-hand rule, cross product rule. Rule number 4, x-axis must intersect the Z-axis of the frames before it. Kinematic diagram, section 3, parameter and variable. First parameter A. A is the distance from the previous joint point. So here, as you can see, the A1 is from the base to the revolute joint location. So it's from here to here, that would be A1. A2 from this joint point to this point, that would be A2. But here you actually go to here, there is actually extra direction over here, that it would be A3. And A2 is over here. There are extra distance from the joint you have here to the rotator here. Because right here, you append another plate. So this one from here to the end effector, that will be A4. So basically we have A1, A2, A3, A4. So basically the system is A1 like this, A2 like this, A3 like this, A4 like this. And each one of them is perpendicular. That is the A parameter, the distance from the previous joint. Second one is the parameter angle of the Z joint to the previous X axis. So right here, we have a revolute joint over here, and its X direction is right here. So X action is right here. Regularly, we may have Z direction that's perpendicular to it. And then the rotator direction is actually on here. The rotator is like this. But this one, you may have some angle. Say its angle may be like this. So there's a certain angle between your vertical direction and the real direction. So over here, you will have your Z direction, Z1, originally from here, now actually changed to here. So that angle that deviate from your original direction, 90-degree perpendicular direction, this one will be your alpha. That's the angle of the Z joint to the previous x-axis. Example robot arm number 2. So this one, you have a revolute joint over here, and you have A2 over here, A3 up to here. And then since this one can be pushed, so this one actually is a prismatic joint. So the distance from here extended to outside for your extender and for your end effector. So basically this distance from your 0 to where you extend, that is the variable D. We will see these, the variable from the joint in the prismatic arm. So this one is the robot arm number 2. Let's look at joint variable. The value that changes when the joint moves is called a joint variable. Joint variable have 2 types. Number 1 is the angle. So here, because my robot can be moved on my revolute joint number 1, it can move this way, make circle like this. So this rotation is called angle theta. That's our first joint variable. Second one will happen on this prismatic joint. And the distance that it can extend is called D. That's the displacement D is another joint variable. So 2 joint variable, theta and D over here. And 2 possible distance when you design your frame. One is for distance from your previous joint. The other one is your angle of your joint. Section 4, Danavik-Hartenberg parameters. So here you can see this Danavik-Hartenberg parameter for a 3-joint robot arm and 3 links. And here has the matrix for different link location. This one you can look at the text lecture and figure it out. Danavik-Hartenberg frame. A kinematic diagram is a kind of joint that is used in robotics to find the equation we need to control over robot manipulators. In this video, we have investigated several different types of robot manipulator and learned how to draw kinematic diagram matching manipulators. Then you will learn how to draw frames on the kinematic diagram following 4 rules known as the Danavik-Hartenberg rules. Some programming lab activity and quizzes may follow this dry lab video. Demonstration. Kinematic diagram for arm 3. Here we have a arm 3. So let's look at this arm 3. We basically has a revolute joint over here. We have a second revolute joint over here. And the end effector is over here. So first one, let's look at A. A would be the distance from the base to here. That would be A1. A2 would be from here to here. That's A2. A3 will be here to here. That's A3. A4 is here to here. That's A4. Theta number 1. Theta number 1 will be the angle you rotate from here. So basically, you need to set up your Z direction over here. And then your X0 direction. X1 direction over here. And your Y direction, because this one is more plenary, so you have to look at it more in a right-hand rule way. And another theta joint variable over here. Okay, there's no D variable, displacement joint variable. So this actually is the diagram for our robot arm number 3. Our X-arm robot can also be modeled with the kinematic diagram. So let's look at it. Our robot actually has 6 different servos. So that's based on the servo 6. It is the base. On top of it, we actually build a solid block. And on this solid block, we actually have servo 5 that would be a revolutional joint number 1. That is servo 5. Servo 6 is a rotator. And then you would have joint 4, the servo 4, and then servo 3. And then there is a arm over here, and that one actually has an end. And then there is a servo over here, but it do rotator over here. And then on top of it, you have your fingers. And finger can actually do release or close. So this servo 1 for finger, actually, it is nothing to do with the kinematic diagram. And servo 2, the same thing, it actually is the end effector. So end effector is over here, and it actually won't change because your fingers is nothing to do with its motion, okay? It's just open or release. So basically we have 3 rubber root joints over here, and 1 do planary rotation. So 1 plane rotation, the other 3 perpendicular to it. Okay, so that is our robot model. So let's look at the XYZ direction. So the first one, you actually do rotation. So the Z0 will be here. And then your G1 actually is over here. G1 is over here. Your G2 also over here, the rotator. These 3 also over here. So basically, it is quite simple. The model is quite simple. And X direction, you can define the X direction. And I don't think that X direction matter too much. And the A and D displacement, they basically is no displacement or prismatic joint. They are all revolute joint, and each one is described by the angle. And the close and release is not in the kinematic diagram model. Thank you.